Hello, this is a recording of a presentation given at the 8th World Congress on Joints, Bearings and Seismic Systems in Atlanta, Georgia in September 2016. It's about using finite element analysis to computationally model joints, bearings and seismic systems. Just a bit of background first. LUSAS has its headquarters in the UK and has a global presence, and I work out of our New York office. For over 35 years, LUSAS has been at the forefront of finite element technology and has its origins in what is now part of Imperial College in London, one of the top engineering universities in the UK and part of London University. We concentrate on the development, marketing and support of high-quality specialist engineering analysis software, in particular for the construction industry. We also have an engineering consultancy division which offers specialist finite element consultancy services. And for those that are wondering, LUSAS is an acronym of London University Structural Analysis System. So LUSAS offers a range of engineering analysis software products that covers the following applications: bridge engineering, civil and structural engineering, composites, teaching, research for use in academia, general mechanical engineering and specialist applications such as geotechnical analysis, that sort of thing. They all provide accurate and reliable solutions for all types of linear and non-linear stress, dynamic and thermal or field analysis type problems. So what is finite element analysis? At the most basic level, it is a technique for analysing structures. It's about notionally cutting up the continuum of a real structure into small elements connected at nodes which can be handled mathematically. The principle of subdividing a structure like that can be applied to structures of all forms and complexities, but it's not for analysing fluids or mechanisms. So what about joints and bearings? Where do they fit in? They often behave like mechanisms. They slide and can't really be represented by elements which are fully connected to one another, and this causes problems. Indeed, the LUSAS support desk helps thousands of engineers each year looking at failed analysis and unexpected results from models sent in. Gross errors in boundary conditions are amongst the most common causes of misleading results. Crude assumptions for boundary conditions are amongst the most common causes of misleading results as well. So whilst engineers may spend weeks constructing elaborate finite element models, they often overlook boundary conditions to the extent that they are actually forgot to add any supports to their model at all, or they make crude assumptions such as treating supports to be infinitely rigid. Nothing is infinitely rigid. Bridge deck behaviour, probably the most famous book on grid analysis, was about the modelling of the bridge deck rather than the whole system. But Hambley, the author, could see the problem and he wrote, "It is important to devote as much care to the assessment of the stiffness of the supports and foundations as to the stiffness of the deck structure." And a simple example illustrates this. This is a skew slab on elastomeric strip bearings. An assumption of rigid supports in a linear elastic analysis could overlook uplift and give misleading results. An assumption of rigid supports with lift-off behaviour is still rather crude and can overestimate uplift, giving different misleading results. Including the support stiffness in the analysis model is fundamental if we want to get results which reflect the real behaviour of the structure. The structures we build generally include a wide range of joints and bearings for various purposes, like regular bridge bearings which accommodate temperature movements, as well as half joints, pin and hanger joints and so on, and vibration control devices applicable for seismic excitations, or perhaps wind turbulence or pedestrian excitation using dampers or isolators. Or perhaps bearings which rotate or slide to allow movement of a heavy structure, like this one, to allow shipping through. But how we deal with all these joints, bearings or devices analytically falls generally into two categories. First, local analysis. The purpose of a local analysis is to discover the behaviour of the device subject to certain loading or excitation. For that, we would typically use continuum elements, either 2D or 3D. And this kind of model usually requires a contact algorithm enabling the software to track the interaction between the components making up the device. In this model, the relative displacements of the parts and the stresses in any part of the device can be determined based on the identified points of contact across two slip planes. The first being the lower concave dish and the slider above, and the second being within the articulated slider on the top of the dome. Alternative to a local analysis is, of course, a global analysis. The purpose here is to replicate the behaviour of the bridge, building or structure. We will include devices such as bearings and dampers within the system as a whole, usually using joint elements. Joint elements have two nodes connecting parts of the structure or connecting the structure to Earth, and joint elements have their own dedicated mathematical model conditioned to respond with deflections and accelerations based upon a real device. This might include damping and hysteresis. The designers of the Gateshead Millennium Bridge in the UK, Ramboll, used both a local model to investigate the mechanical bearings and a global model for the bridge as a whole. Global models may require joint elements for movement, like this one, or simply for bridge articulation. This global steel truss bridge has two hanger joints supporting the drop-in centre span. The correct articulation of the bridge, when subject to a moving load as seen here, can be modelled using a simple joint element. The rotations at the joint mustn't exceed a design value, and the model can be used to check for that. In extreme conditions even, the joint could reach its maximum rotation and become jammed, and a joint element can be given suitable properties to model that sort of change in behaviour as part of a nonlinear analysis. Simple nonlinear joints available in software such as LUSAS include elastoplastic behaviour and smooth contact joints with, if required, initial gaps, and frictional joints, again with initial gap as needed. And joint materials like these may also include thermal properties along with mass and damping properties to suit dynamic analysis requirements. Smooth contact or frictional joints may be used for lift-off or hook type contact problems as well. Foothills Bridge made a global model of the San Francisco Oakland Bay Bridge with its hanger joints. A really comprehensive model for this large dismantling project. Here you see the animation of the dismantling. A fantastic deconstruction sequence case study which you can read about on our website. Here you see a series of images of the dismantling sequence. For the new Broadway Bridge in Little Rock, Arkansas, designed by HNTB, the two 440-foot steel basket handle arches will be constructed on top of falsework on barges and floated into position. When the barges are flooded and the bridge is brought to rest on their permanent end bearings, the deck tends to elongate and, depending on the friction in the temporary bearings, as you can see these yellow ringed areas here, this can set up some design critical load effects in the temporary towers. Genesis Structures carried out the erection engineering using frictional contact joints between the deck and the towers, and this ultimately led to a less conservative, cheaper but safe design for the towers. Genesis Structures were also employed by Massman Construction to model the surgical deconstruction of the Paseo self-anchored suspension bridge in Kansas City, Missouri, next to the new KC Icon cable stay bridge. Here you can see the cable lowering sequence with the cables being moved in two planes, and the saddles at the top of the towers, details of which you can see here, supported the main cables and translated 4.5 inches during construction back in 1954. They were then locked down with steel plates. During the working life of the bridge, the deck was replaced and bearings raised, so a LUSAS model was built of the saddles using joint elements to help predict the locked-in stresses and the potential movement once the steel plate was cut in the deconstruction sequence. Jacks were put into place, and the plate cut, and the jacks slowly released. The actual movement was as predicted in all the saddles within 1/4 of an inch, and the bridge was safely dismantled. This dry dock in the UK was to be used for the refit of nuclear submarines. It is closed by floating this massive reinforced concrete caisson into place, sinking the caisson, sealing the joint along the bottom and sides, and then draining the dock. Obviously, once the work on the submarines is underway, nothing must cause a breach in the caisson, not even a rare English earthquake. And so a part of the safety case for this work was to analyse the caisson with frictional non-linear contact joint elements, modelling the shear key connection and also modelling the potential uplift from subgrade. A time history analysis was carried out with steps of 0.005 seconds, and here we can see the liftoff and recontact vectors and the axial force in the caisson when the strong motion occurs between 3 and 4 seconds. You can see the clock ticking over at the bottom there. The hydrodynamic force from water enclosed in the cells was simulated using more joint elements to provide hydrodynamic mass against the walls and for damping actions on the base interface. The walls and the base themselves were modelled using shell elements, and the analysis clearly showed the caisson had adequate structural capacity to withstand a seismic event and that the seals could accommodate the displacements expected. This seismic assessment was mostly about movement or liftoff. For many seismic analyses, it's necessary to go way further in terms of modelling specific seismic isolators. These more complex bearings exist to control the damage impact of seismic activity on structures. The bearings are used principally for seismic isolation, energy dissipation, or to model an active control system. They all exhibit hysteretic behaviour, which is that highly nonlinear phenomenon that occurs in systems that possess memory. 3 principal types of isolator are available, including high damping rubber bearings, the most commonly used elastomeric bearings, lead rubber bearings with plastic yield and biaxial hysteretic behaviour, and sliding frictional pendulum systems which have pressure and velocity dependent friction coefficients and biaxial hysteretic behaviour. The single friction pendulum bearing, or the multiple multispherical derivatives, such as the triple friction pendulum bearings, are the most widely used passive seismic isolation bearings in the United States. These allow an adaptive force deformation behaviour, hence adaptive seismic isolation, whereby stiffness and damping properties of the bearing can change at predetermined displacement amplitudes. Likewise, LUSAS allows for the inclusion of viscoelastic dampers, such as the 4-parameter solid model shown here, which comprises up to 3 springs and a dashpot. So these non-linear isolators and dampers can be included in a global analysis, as they have been in this 1,108 metre, or over 3,600 foot long, multi-span pre-stressed concrete road bridge structure in the Mediterranean region. This enables design forces arising from an earthquake, such as the recent 2016 quake in Italy, to be assessed to Eurocode EC8. This bridge has an expansion joint midway along its length. It was modelled with engineering thick beam elements, or Timoshenko beams, defined at the respective centroid of each structural component. Connection between deck and elastomeric bearings, and between the top of the piers and the elastomeric bearings, was made using nominally stiff members of negligible mass. These represented rigid links between the centroids of components and were defined with negligible mass so as not to contribute to the dynamic behaviour of the bridge. 2 longitudinal dampers were located at the first abutment and transverse dampers located at every 3rd pier along the bridge, which required an additional stiff member arrangement. Eigenvalue analysis on both bridge structures found that 225 structural modes were required to meet the 95% mass participation factor value prior to carrying out subsequent spectral response analysis using EC8 design spectra. 3 nonlinear transient dynamic analyses were performed on each bridge using combinations of acceleration time history dataset pairs in the longitudinal and transverse directions as used by the bridge designers. The bottom right image shows a typical transverse force time history plot produced. Good correlation of results was achieved for both the spectral response and the transient dynamic analysis, verifying the modelling techniques used by the original designers and the viscous damping capabilities of LUSAS. A similar global model was used to define a retrofit strategy for the Milford-Montague Truss connecting New Jersey to Pennsylvania across the Delaware River to accommodate the demands of seismic and temperature effects. This included elastoplastic lock-up devices at the Montague abutment and guided isolation bearings at the piers. The existing fixed bearings were retained at the other abutment. The isolation bearings transfer longitudinal loads from the piers to the truss, and the lock-up devices evenly distribute this load between the abutments. This bridge project was subject to a paper presented at the 5th National Seismic Conference by Tom Murphy and Mike Irwin and is available on the web. So in general, global analyses often include joint elements to model the behaviour of specific bearings or damping devices, and joint elements have been developed to represent all kinds of device or structural arrangement for pushover analysis, large displacement analysis, and transient analysis. These are invariably hysteretic and can represent, for example, the behaviour of structural connections such as reinforced concrete, steel, and timber. There are a wide range of these joint types available in LUSAS, as seen on these slides, such as the last one here, the Fukada degrading trilinear hysteresis for modelling plastic hinges in reinforced concrete beams, which changes stiffness at cracking and yielding points. Obviously, those many joint material models have been developed with specific purposes in mind, and there are more details in the LUSAS manuals. But if we think back to local analysis, although joint elements are able to model contact and liftoff, where there are elements moving right over one another with relatively large displacements, a contact algorithm, known as a slide line, or in 3D a slide surface, is a more powerful computational tool. This example uses a frictional slide line which shows very clearly how contact is transferred from element to element. It's actually a floating pontoon restrained by cables to 2 anchor blocks sitting on a riverbed. We can see that the cable becomes taut and the left block starts to be dragged along the riverbed with elements coming into and out of contact. This isn't something you could reasonably model with joint elements, so it requires a contact algorithm to detect which elements are transferring stress to which other elements in potentially very highly nonlinear situations, including dynamic analysis. Indeed, you can see that in this local model. Frictional joint elements were used around the pin, while many other contact surfaces were included in the model by use of contact slide lines. This is a pin joint in the turning torso building in Sweden. Most of the local model here is of course built with 3D continuum or solid elements. These other joints are similarly local models constructed using 3D solid continuum elements and using contact slide surfaces to give a realistic response to whatever loads or displacements are applied to the various components. Even back in 1995, bearings were being analysed using 3D continuum and nonlinear finite element analysis. UK consultant Hyder, who now Arcadis, had to carry out collapse analysis of fabricated steel trestle bridge bearings as used on the M5 concrete road bridge in Avonmouth. Initial FEA models assessed the performance of both shell and solid element idealizations, with final all-solid models including geometric, material, temperature, and contact nonlinear effects. With the experimental data, load strain measurements, very close agreement between measured and calculated values of ultimate load could be seen. The analysis also clearly showed that the failure mode was plastic collapse, with elastic buckling occurring at a much higher load. Results were used by Hyder to help determine which bearings would require strengthening for increased bridge capacity. Then, whilst traffic was traversing the structure, they had to ensure that the strengthening modifications, which consisted of welding an additional plate onto the sides of the bearings to stiffen them, were safe and effective. Similarly, non-linear continuum models were used to assess the half joints, sometimes called dapped ends, for the existing Kingston Bridge in Glasgow, UK. Half joints were introduced into concrete decks as a means of simplifying design and construction operations, but they are a corrosion trap, particularly susceptible to chloride attack, and not easily accessible for inspection or maintenance. In addition, on older structures, the half joints, as designed, may not even be code-compliant with today's standards and may require assessment for increased modern vehicle loadings. This bridge carries an average of around 180,000 vehicles a day, one of the busiest in Europe, and it includes many half joints designed to standards in the 1960s. An assessment showed that some of the half joints were not compliant with modern codes, and so FEA models were built and then validated with a destructive load test on a typical joint in a ramp that was being demolished anyway and replaced as part of other work taking place on the structure. The test and the corresponding FEA model agreed and showed significant spare capacity for the joint. This gave the designers AECOM confidence to reassess all the remaining half joints in the bridge, eliminating what could have been incredibly costly and disruptive replacement works. This sort of analysis can involve not only continuum analysis and slide lines, but also other non-linear functions. In this case, the LUSAS concrete cracking and crushing material model, as shown in the illustrative half-joint analysis here. It's probably one of the most advanced non-linear concrete material models in the world today. It's been validated against all kinds of experimental data, and this model even includes cracking, crushing, aggregate interlock, and remembers unloading and reloading. It also gives predicted crack widths under load. More recently, AASHTO commissioned research into span lock behaviour by Hardesty and Hanover. One of the test structures was the Hillsborough Avenue Bascule Bridge in Tampa, Florida. The analysis examines stresses in the lock bar system, including the lock bar, the guides and receivers, and the shoes in the guides and receivers that contact the lock bar. The local model of the lock bar is using 3D continuum and contact slide surfaces. It's embedded within a larger global model which comprises thick shell elements and Timoshenko beams. This avoids the transfer of data between global and local models, retaining the accuracy in the area of interest and the efficiency of a global model for the remainder of the structure. The bridge was also instrumented to confirm the behaviour of the finite element model, and so now the model can be adjusted to analyse a multitude of different lock bar designs. And so we've seen how joint elements can be used in global models to represent all manner of interfaces and devices, from simple pin joints to advanced seismic isolators. Local models with contact slide lines can enable study of devices, and the two can be combined within a single model for efficiency. Also incorporating other forms of nonlinearity such as concrete cracking, soils or large displacements as required. I hope this has given you an introduction to how finite element analysis can help you. Thank you for your time, and if you have questions, please ask through our website.